The Great Pyramid of Giza aligns with true north within a tiny fraction of a degree. Ancient engineers created perfect symmetry across the globe without a single modern tool. This video will show you precisely how they did it, revealing forgotten methods that challenge our ideas of progress. You will discover how celestial patterns, simple ropes, and profound geometry built monuments that still baffle us today. How did they achieve such accuracy with what seems like so little? What deep understanding of the world allowed them to turn stone into timeless harmony? By the end, you will see ancient engineering not as a mystery, but as a masterclass in human ingenuity, offering powerful lessons for our own future. How much of their wisdom have we left behind in our rush toward technology? This universal harmony began with a single step: the creation of a reliable unit of measure. Ancient engineers did not see the world as a collection of separate parts, but as one interconnected system. The same patterns that guided the stars across the night sky and the changing of the seasons were also the blueprints for their temples and cities. To build in tune with this cosmic order, they needed a measurement system that was itself born from nature. They found it in the most accessible of places, the human body itself. The cubit, for example, was the length from a man's elbow to the tip of his middle finger. This was not a random choice. It was a unit anyone could carry with them, a built-in standard that made every worker a living part of the project's geometry. But these measures went far beyond simple practicality. The Egyptian royal cubit, meticulously standardized with a physical rod of granite, was also deeply symbolic. Historical research suggests that the architects and priests of the time understood profound geometric relationships. They knew, for instance, that the length of the royal cubit could be connected through a specific sequence of calculations to the actual circumference of the Earth. This means that a unit used to lay a single stone block was, in their view, a direct reflection of the entire planet's dimensions. As experts like archaeologist John Romer have pointed out, this was not an arbitrary system. It reflected a core belief that a cosmic order existed, and the highest purpose of engineering was to mirror that perfect order here on Earth. By grounding their work in the observable realities of the human form and the heavens above, these builders achieved a level of precision that can seem almost supernatural to us today. Yet it was not magic, it was empirical knowledge refined over generations. They used what was consistently and reliably present, turning the human arm and the celestial cycles into the most sophisticated tools imaginable. This foundational approach raises a powerful question for our own time. In our rush to rely on complex technology, have we forgotten how to see the simple, effective solutions that nature provides all around us? This deep, integrated understanding of measurement set the stage for the incredible techniques that would follow, turning abstract harmony into enduring stone. That same human scale measurement found its ultimate purpose under the night sky. Without a magnetic compass, ancient engineers turned to the heavens for their most critical reference, true north. An astronomer priest would have spent countless clear nights observing the slow, predictable dance of the stars, particularly the circumpolar stars that never set. By marking the points on the horizon where a specific star rose and set over the course of a year, they could bisect the angle to find a fixed north-south line with astonishing accuracy. This was not a quick process. It required patience that spanned seasons, a deep commitment to recording the cosmos with nothing but the naked eye and simple tools. In Egypt, they used an instrument called a merkit, a narrow bar with a plumb line that acted like a celestial sighting tool. A second priest would place his merk hit some distance away, and together they could align their instruments on a single star, translating its perfect path in the sky into a perfectly straight line on the ground. This is precisely how the Great Pyramid's builders achieved an alignment to true north within just 1/15 of a degree. The pyramid's base is not merely square, it is a terrestrial mirror of celestial order. At places like Stonehenge, the same principles were at work. The massive heel stone aligns with the summer solstice sunrise, an event that could be predicted and marked year after year, turning the entire monument into a giant astronomical calendar. This long-term perspective is almost unimaginable today. These were projects that required the dedication of multiple generations, each one building upon the precise observations of the last. What does such patience say about a culture's relationship with time itself? They were not building for a single lifetime, but for an eternity they believed was written in the stars. This celestial mapping provided the unshakable foundation, the first and most important line from which all other symmetry would grow. With a perfect north-south line etched into the desert floor, the next challenge was to build upon it with flawless geometry. The solution was not found in complex machinery, but in the elegant application of simple ropes and weights. Egyptian surveyors would take long cords, often soaked in water to prevent them from stretching under the sun, and use them to lay out perfect right angles. They employed the 3-4-5 triangle method, a practical use of the Pythagorean theorem centuries before the philosopher gave it a name. By measuring out 3 units on one rope, 4 on another, and ensuring the diagonal between them was exactly 5 units, they could create a perfectly square corner every single time. This was geometry in its most powerful form, transformed from an abstract idea into the very cornerstone of a pyramid. For vertical precision, they relied on the Plumb bob, a simple weight suspended on a string that always points directly toward the Earth's center. This tool ensured that every massive block of stone was set perfectly upright, that the towering walls would rise straight and true for generations. To establish a level plane across vast foundations, they used water channels. Because water always finds its own level, these simple trenches became a universal standard for flatness, allowing teams working hundreds of feet apart to build on the same perfectly horizontal base. This combination of ropes, weights, and water provided an infallible toolkit. This geometric wisdom was not confined to Egypt. In Mesopotamia, engineers recorded complex problems of land division and city planning on clay tablets, proving an advanced grasp of proportionality and area. They used these principles to construct massive ziggurats, whose precisely angled sides reached for the heavens. In ancient Greece, the same fundamental tools allowed for the creation of vast, circular theaters where every seat had a clear line of sight to the stage, a masterpiece of acoustic and visual planning achieved with little more than a rope and a stake. Perhaps the most refined application of this knowledge is seen in the Parthenon. Its famous columns are not actually straight, they curve slightly inward. The platform itself bows almost imperceptibly in the center. The architects understood that perfectly straight lines would appear to sag to the human eye, so they introduced these gentle curves to create the illusion of perfect straightness. This was geometry elevated to an art form, a deep understanding that measurement must sometimes partner with perception to achieve true harmony. It makes you wonder, in our age of laser levels and computer modeling, what have we lost of this intuitive, tactile connection to our materials? These ancient low-tech solutions were inherently sustainable, using readily available resources and fundamental physics to achieve results we still struggle to replicate. Their work challenges us to reconsider what is possible when we truly understand the principles at play, rather than just the complexity of our tools. This mastery of basic geometry provided the essential framework, the the stable skeleton upon which the most breathtaking architectural artistry could then be layered. Yet this geometric precision was only half the story. The true soul of these ancient structures lies in the silent language of proportion, a system of harmonic ratios that makes a building feel instinctively right. An architect designing a Greek temple did not rely on rulers alone, but on the golden ratio, a number approximately equal to 1.618. This ratio dictated the relationship between the width and height of columns, the spacing between them, and the dimensions of the triangular pediment above. The result is a visual harmony that feels as natural as the spiraling pattern of a nautilus shell or the arrangement of seeds in a sunflower, patterns we now know are described by the Fibonacci sequence. This was not merely decorative, it was a profound belief that the same mathematical order governing the cosmos should be reflected in human creations. From the Parthenon in Athens to the soaring Gothic cathedrals of medieval Europe, this principle of universal beauty was encoded into stone. To achieve this consistency on a massive scale, ancient engineers used modular systems. They would define a single base unit, perhaps the diameter of a column, and then design every other element as a multiple or a fraction of that unit. This ensured that even the most complex structure maintained a perfect, repeating rhythm, a symphony of stone where every part related to the whole. The Roman architect Vitruvius famously wrote that a well-designed building should mirror the proportions of the human body with its harmonious symmetry. This philosophy went far beyond aesthetics. A structure built with these harmonic ratios often possessed a hidden structural integrity. The balanced distribution of weight and stress across a framework governed by natural proportions could make a building remarkably stable and resilient, a perfect marriage of beauty and strength. This ancient wisdom forces a powerful question for our own era of algorithmic design and computer optimization. In our pursuit of maximum efficiency, have we lost touch with the innate, biological sense of balance that these ratios provide? What might we gain by relearning how to design with the proportions that nature itself has perfected over millennia? This intimate knowledge of geometry and proportion was brought to life by a mastery of the materials themselves. High in the Andes, stonemasons at Sacsayhuaman fitted colossal granite blocks together with a precision that defies belief, where the joints are so tight that not even the thinnest blade can find a gap. This was not brute force, but a profound collaboration with the stone. They understood how to read the natural grain of the rock, using simple yet brilliant techniques like driving dry wooden wedges into fissures and then soaking them with water. As the wood expanded with immense, steady pressure, it would cleanly split the stone along its weakest plane. With harder stone tools and patient abrasion, they then shaped each block into its perfect interlocking form. This deep material wisdom guided every decision. Engineers would often journey vast distances to quarries, seeking out specific types of stone known not just for their strength, but for their workability, for how willingly they responded to these ancient methods. In Egypt, the evidence is etched into unfinished obelisks. The drill holes and saw marks left by bronze and copper tools reveal a process that was painstakingly slow. Teams of workers would use a slurry of sand and water with a simple copper saw, the abrasive grit doing the real cutting through days and weeks of relentless, careful motion. Speed was never the goal, only the flawless execution of a preordained design. This philosophy resulted in constructions that needed no mortar. The sheer perfection of the fit created joints that locked together under their own immense weight, relying on gravity and friction to create structures that have withstood earthquakes for centuries. Can you envision the mindset required for such work, where a single block might represent months of a craftsperson's life? This stands in stark contrast to our modern world, where construction prioritizes speed and replaceable components over timeless integrity. The cumulative power of this unhurried craftsmanship was a total freedom of design. Architects could plan the most complex, gravity-defying forms with absolute confidence, knowing the artisans could translate those plans into reality, one perfectly placed stone at a time. This deep, tactile partnership with materials set the stage for the final, and perhaps most mysterious, ingredient in their success. A miniature clay palace, complete with intricate courtyards and stairways, survives from Minoan, Crete. This was not a child's toy but a master architect's three-dimensional blueprint. Across the ancient world, from the royal workshops of China to the drafting rooms of Egypt, engineers built scale models from wood and clay to test their most ambitious ideas. These prototypes allowed them to see a structure in the round, to identify points of weakness in load distribution or alignment long before a single foundation stone was laid. It was a form of risk management as sophisticated as any modern computer simulation, relying on tangible, hands-on experimentation. In Egypt, this preparatory genius extended to two-dimensional plans. A grid system, meticulously painted onto a wall, served as the guide for sculptors. A small, perfect sketch of a pharaoh could be scaled up to a colossal statue by simply following the squares, ensuring that every proportion from the curve of a smile to the set of the shoulders remained harmoniously intact when enlarged to a towering scale. This systematic approach required meticulous record-keeping. Mathematical calculations detailing dimensions, angles, and material quantities were recorded on papyri and clay tablets. These were the ancient equivalent of a project manager's briefing, providing clear instructions for foremen overseeing vast teams of laborers. This level of organization was the true backbone of these monumental projects. It allowed for the coordination of hundreds, sometimes thousands of workers, each team focusing on a specific segment with the absolute confidence that their piece would fit perfectly into the grand preordained design. What does this reveal about these ancient societies? It shows a capacity for complex logistics and long-term project management that rivals any modern corporation. They understood that the chaos of raw construction had to be tamed by order long before the first stone was ever quarried. This entire process, from the clay model to the wall grid, was powered by a silent, formidable engine, a deep and practical command of mathematics that wove numbers directly into the fabric of their world. This mathematical genius was not confined to one corner of the globe. In the dense jungles of Mesoamerica, the Maya developed a numeral system so advanced it rivaled any in the world. Their system was videsimal, meaning it was based on 20, and it included a fully formed concept of zero, a profound abstract idea that would not appear in Europe for centuries. This was not merely for counting, it was the engine for an astronomical science of breathtaking precision. With it, they could calculate the cycles of Venus, predict solar eclipses, and align their towering pyramids to capture the sun's rays on the equinoxes, transforming stone into a cosmic calendar. Their temples were not just buildings, they were three-dimensional expressions of mathematical truths, their symmetry echoing the predictable order they saw in the heavens. Far across the world, in ancient India, mathematicians composed concise sutras, poetic verses that encoded complex rules for geometry and algebra. These principles were not kept in isolated academic texts, they were the living blueprint for master builders. At the temple complex of Khajuraho, every soaring spire and every intricately carved panel follows a strict geometric code. The entire structure is a symphony of interlocking triangles, circles, and squares, a fractal harmony achieved because the architects could precisely calculate angles, areas, and volumes from a shared sacred framework. This was mathematics made manifest, a divine language written in stone. Even in Egypt, the practical application of math is undeniable. The Rind Mathematical Papyrus, a scribe's training manual, contains problems directly related to pyramid construction, showing how builders calculated the slope of a face or the volume of stone needed. They used methods like triangulation for surveying vast tracts of land, and some historians suggest they even used an early form of calculus to approximate the constant pi for circular structures. This deep knowledge was often esoteric, carefully guarded within priestly classes or stonemason guilds. The technical expertise for aligning a wall was inseparable from the spiritual ritual that consecrated it. How might this fusion have enhanced the structure's perceived perfection? For the community, a temple was not merely an engineered object, it was a living entity, its flawless symmetry a direct reflection of cosmic order and divine favor. The mathematics ensured that every angle and every proportion resonated with a deeper, universal truth, making the building feel inherently sacred. This profound integration challenges our modern separation of science and spirit. It suggests that the ultimate perfection of these ancient wonders came not just from calculation, but from a culture that saw no dividing line between the precision of numbers and the poetry of belief. This drive for geometric perfection was fueled by a profound cultural imperative. For ancient societies, symmetry was far more than a pleasing visual. It represented the fundamental order of the universe itself. In Egypt, this concept was known as Mat, a principle of cosmic balance, truth, and harmony that governed everything from the seasons to the stars. The perfectly symmetrical layout of their temples was a deliberate attempt to build a little piece of that divine order here on Earth. The temple was not just a building, it was a machine for maintaining cosmic stability. Its balanced forms a daily prayer for the continuation of the world. Across the ocean, the pyramids of Mesoamerica were conceived as sacred mountains, their precise stairways and terraces echoing the mythic landscape of creation. Their alignments were not arbitrary, they were physical manifestations of celestial pathways, designed to connect the human world with the realms of the gods. This made accuracy a spiritual necessity. A misaligned temple was not just an engineering failure, it was a theological one, a crack in the very fabric of reality. This is why a site like Newgrange in Ireland was constructed with such care. Its long, narrow passage is oriented so that for a few precious minutes at dawn on the winter solstice, a single shaft of sunlight pierces the inner chamber, illuminating the ancient resting place within. This annual event was not a happy accident. It was the entire purpose of the monument, a guaranteed miracle of light and shadow made possible by flawless celestial alignment. Such projects required the full support of the entire society. They were often directed by the highest religious or royal authorities, who provided the vast resources and long-term vision. The pursuit of architectural perfection became a form of worship, a demonstration of a ruler's power to enact divine will in stone. This collective belief enabled the kind of generational collaboration we see at Stonehenge or in the Great Pyramid, where hundreds of workers labored for decades with a shared sacred goal. It forces us to reflect on our own motivations. In our modern world, what cultural or symbolic imperatives drive our greatest technological leaps? Are we building for short-term profit or for a legacy that resonates with deeper meaning? This shared cultural vision provided the final, crucial element, the social cohesion that turned brilliant individual calculations into enduring monuments for the ages. A massive Roman aqueduct did not rise from the efforts of a single crew, but from the coordinated labor of teams who may never have spoken the same language. This was made possible by an empire-wide system of standardization, where a unit like the Roman foot was not a suggestion, but a law. From the damp quarries of Britain to the sun-baked hills of North Africa, every craftsman used the same measure, ensuring that an archway carved in one province would fit perfectly into a bridge being built 1,000 miles away. This created a kind of industrial harmony where complex projects were assembled from interchangeable parts with breathtaking efficiency. This principle extended to every tool in the workshop and every lesson in a stonemason's training. Manuals like Vitruvius's De Architectura codified this knowledge, providing a universal reference for everything from the ideal proportions of a column to the proper mix for hydraulic concrete. It was a shared technical language that allowed expertise to be replicated and preserved across generations. For cultures without a written script, this communication took even more ingenious forms. High in the Andes, the Inca administrators used the quipu, a complex array of knotted cords. While its full purpose remains debated by scholars, these intricate textiles likely recorded more than just census data or tributes. The patterns of knots, their positions, and the colors of the strings could have encoded the very specifications for a terrace wall or the logistical needs for feeding a workforce of thousands. A single quipu, carried by a swift runner along the empire's vast road network, could transmit a complex set of instructions without a single written word. This relentless focus on clear standards and effective communication was the invisible architecture behind the physical one. It drastically reduced the errors that naturally arise from individual interpretation, ensuring that a technique perfected in the capital could be executed with consistent quality at the farthest frontier. This organizational genius raises a critical question for our own globally connected projects. With all our digital collaboration tools, do we truly share a common language, or are we often building with incompatible systems that create waste and confusion? The ancient model shows that true scale is not achieved through sheer force, but through a unified framework that empowers every participant to contribute their skill toward a single, flawless whole. Behind every perfectly placed stone was an invisible architecture of human organization. The construction sites of ancient Egypt functioned with the precision of a modern city, where thousands of individuals were not a chaotic crowd but a coordinated body with specialized roles. Quarrymen, recognized for their unique skill in extracting stone along its natural grain, formed one team. Transport crews, experts in moving colossal weights on sleds and rollers, formed another. Artisans dedicated to the final carving and finishing worked in their own designated areas, while scribes meticulously recorded every transaction, from tool distribution to daily bread rations. This clear division of labor was a masterstroke of efficiency, allowing each person to develop a deep, almost intuitive expertise in their specific task. Master builders, the project managers of their day, moved between these teams, holding wooden cubit rods and papyrus plans to ensure every block met the exact design specifications before it was ever set in place. This system ensured that the project advanced not as a series of guesses, but as a seamless, integrated process. Far to the east, in Mesopotamia, clay tablets etched with cuneiform script reveal an equally sophisticated administrative machine. These ancient spreadsheets detailed the precise allocation of barley, oil, and wool to the workforce, proving that supporting thousands of laborers was a calculated logistical operation, not a haphazard effort. This immense manpower was often drawn from agricultural communities during the inundation season, when the Nile's floodwaters made farming impossible. This seasonal labor model was a stroke of social genius, providing the state with a massive workforce without crippling the nation's food supply. Coordinating such diverse groups required more than just logistics; it demanded social cohesion. Workers' villages, like those discovered near the Giza Plateau, provided not just housing but also medical care, bakeries, and even breweries. These were incentives, a form of ancient benefits package that fostered loyalty and maintained morale for a project that spanned decades. How does this compare to a modern construction site or a tech company's project team? The principles are strikingly similar: clear roles, resource management, and team motivation. The true engine of these ancient wonders was this seamless integration of human effort, all channeled toward a shared cultural goal that gave every individual laborer a sense of purpose in a legacy meant to last for eternity. That final, perfect fit between two stones was rarely a first attempt. It was the result of an iterative process, a slow and steady dance of testing, observing, and refining. Ancient masons did not simply cut a block and hope for the best. They would place it, then use the simplest of tools, a straight edge of wood or a taut string, to check for any deviation. They felt for gaps, looked for light passing through, and listened for the hollow sound of a poor fit. Then, with stone hammers and abrasive sand, they would shave, grind, and polish, making tiny, incremental adjustments until the block sat flush and true. This was a continuous feedback loop of action and assessment, allowing for the correction of errors in real time, right there on the construction site. We can see this process fossilized in the Great Pyramid's casing stones. While their outer faces were polished to a mirror finish at the quarries, their final fitting against one another was done in place. Slight variations in the joints show how teams worked block by block, adapting to the minute imperfections of each stone to create that legendary seamless surface from a distance. This philosophy of learning by doing extended across entire generations. The evolution of the dome in the Roman world is a masterclass in this accumulated wisdom. The Pantheon's magnificent coffered ceiling represents a breathtaking experiment, a single massive pour of concrete that demanded unheard of confidence. The builders learned from its success and from its subtle stresses. Later Byzantine architects working in Constantinople refined the form. They developed lighter, more buoyant domes resting on pendentives, a solution that allowed for taller, more complex structures. Each project became a living lesson, its successes and failures carefully observed and encoded into the architectural tradition. This knowledge was not stored in a database but passed down through the intimate master-apprentice relationship. A young stonemason learned not just how to hold a chisel, but how to read the grain of granite, how to listen to the sound a block made when tapped, and how to solve the unique problem presented by each new piece of stone. This system emphasized adaptability above all else. When a quarry could not deliver stone of the expected size, or when a foundation settled unexpectedly, the builders on the ground had the authority and the skill to improvise a solution. They were not merely executing a rigid plan, they were partners in the creation, responding to the reality of the materials and the site itself. This stands in profound contrast to our modern world of pre-modeled digital simulations, where a design is perfected in a virtual space long before ground is broken. While this eliminates many risks, does it also distance us from the intuitive, tactile wisdom that comes from direct, hands-on engagement with our materials? The ancient approach trusted the human eye and hand as the ultimate calibration tools, and the cumulative power of that slow, iterative refinement built wonders that have stood for millennia. The final test of an engineer's genius was not just in shaping the stone, but in choosing where to place it. Ancient builders possessed a masterful ability to read a landscape, selecting sites that worked with the environment rather than against it. The Nabatean city of Petra stands as a breathtaking example, its magnificent temples and tombs carved directly into the faces of rose-red sandstone cliffs. This was more than a dramatic aesthetic choice. The natural rock formation provided an immensely stable foundation and acted as a giant thermal mass, absorbing the desert's intense heat by day and slowly releasing it during the cool nights, creating a naturally regulated indoor climate. This was architecture born from the earth itself, leveraging the land's inherent properties to solve structural and environmental challenges in one brilliant stroke. In the monsoon-drenched regions of Southeast Asia, this wisdom took a different form. The builders of temples like Angkor Wat constructed vast, intricate networks of moats, canals, and reservoirs. These were not merely decorative. They formed a sophisticated hydraulic system designed to manage the torrential seasonal rains, directing floodwaters away from sacred structures while storing water for the dry season. The temples themselves were often raised on high platforms, a simple yet effective adaptation that lifted the most critical structures clear of rising waters. This deep understanding of hydrology and climate informed every decision, from the orientation of a building to catch cooling breezes to the strategic use of overhanging roofs for shade. In Mesopotamia, where stone was scarce, engineers turned to the most abundant local resource, the mud of the river plains. They mixed this clay with straw, formed it into bricks, and baked it in the sun, creating the durable building blocks for their ziggurats and cities. This was the ultimate in sustainable practice, using materials available right at their feet, which minimized the immense energy cost of transportation and created structures that were perfectly suited to the local conditions. This profound symbiosis with the environment presents a powerful question for our own era of glass skyscrapers and energy-intensive climate control. In our quest to dominate a landscape, have we forgotten how to listen to it? These ancient engineers did not see the natural world as an obstacle to be conquered, but as a partner in creation, a source of endless wisdom that, when heeded, led to buildings that were resilient, efficient, and beautifully integrated into their place. This reliance on local resources was the final, crucial piece of their sustainable design, a principle that began with the very ground upon which they chose to build. Ancient builders understood that the most ingenious designs emerged from the landscape itself. In the soft volcanic rock of Cappadocia, they did not quarry stone to build upward, but carved entire cities downward, creating churches and homes from the naturally insulating tuff. This lightweight stone was easy to shape with simple tools, yet durable enough to last for centuries, all while eliminating the monumental effort of transporting materials across great distances. This principle of using what was readily available was a universal constant. In the sun-scorched Indus Valley, engineers crafted sun-dried mud bricks, a humble material that provided exceptional thermal mass, keeping interiors cool by day and warm by night. Far to the west, on the island of Crete, Minoan architects framed their grand palaces with sturdy timbers harvested from the nearby forests, creating structures that were both resilient and perfectly adapted to their environment. This was not a haphazard process, but a deliberate science. Ancient engineers conducted what we would now call material testing, carefully assessing the compressive strength of different stones or experimenting with binding agents. In China, they developed a mortar strengthened with sticky rice paste, creating a cement so strong it has survived for over 1,000 years. In Rome, they mixed volcanic ash with lime to create a revolutionary concrete that could even set underwater. This localized, resourceful approach did more than just make construction feasible. It ensured that every structure felt like a natural extension of its surroundings. A temple made from local sandstone would glow with the colors of the regional sunset, while a fortress built from nearby granite would seem to grow directly from the mountain it stood upon. The incredible durability of these sites, still standing after millennia, is a powerful testament to the success of their selective process. it forces a critical question for our modern world, where construction materials are often shipped across the globe at a tremendous environmental cost. How can we relearn this ancient art of local resourcefulness to drastically shrink our own carbon footprint? This deep, intuitive partnership with the Earth's offerings was then amplified by the next stage of innovation, the creation of specialized tools designed to master each unique material. A copper chisel, painstakingly hardened at its edge, became more than a tool. It became an extension of the craftsperson's will. This was the essence of ancient innovation, not inventing from nothing, but refining the everyday into the extraordinary. In the hands of an Egyptian artisan, such a chisel, drawn patiently across limestone with a slurry of abrasive sand, could incise the crisp, enduring lines of a hieroglyph. The tool itself was a masterpiece of material science, its durability carefully managed through constant maintenance in on-site workshops dedicated solely to sharpening and repair. This culture of tool adaptation was a relentless pursuit of precision. For laying out the vast foundations of a city or a temple, Roman surveyors relied on the groma, a beautifully simple instrument. It was little more than a cross-shaped frame with plumb lines hanging from each arm, yet by sighting across the aligned strings, an engineer could project perfectly straight lines and right angles across miles of territory. This humble device literally paved the way for the arrow-straight roads that stitched an empire together, but perhaps the most profound leap came with the mastery of mechanics. The development of the pulley and the lever, principles famously articulated by Archimedes, fundamentally altered the scale of what was possible. A single team of workers, using a clever arrangement of ropes and wheels, could now lift and position stones that would have required hundreds of men using pure muscle. It was a revolution in mechanical advantage, turning immense physical challenges into manageable tasks. These tools were never used in isolation. A set of Egyptian boning rods, simple stakes connected by a taut string, could establish a level plane across a rocky foundation. That plane, verified by the groma's right angles, created the precise geometric stage upon which the pulley systems would then perform their heavy lifting. Every innovation was a piece of a larger puzzle, each one enabling the next level of complexity and refinement. This relentless ingenuity forces a powerful question about our own relationship with technology. Does our reliance on increasingly complex and opaque machinery distance us from the fundamental principles that these ancient engineers understood in their bones? Their creativity was not about replacing human effort, but about amplifying it, about crafting the perfect interface between intention and material to achieve a harmony of form and function that still defines our idea of perfection today. A single rope stretched taut between two stakes became the ancient world's most versatile drafting tool. For the builders of monuments like Stonehenge, the process began with a central post and a long cord. By keeping the cord perfectly taut and walking a full circle, a team could etch a flawless ring into the earth, a perfect geometric shape born from a simple rotation. This was not the end of the design, but its foundation. Using that same cord, they could mark off specific lengths to plot the positions of standing stones or inner rings, creating the complex concentric patterns that have captivated us for millennia. The same principle was used to stunning effect in Athens for the Tower of the Winds, where a string and peg circle was subdivided to form its precise octagonal base, a shape that required an advanced understanding of angles and chords. This string geometry was a deeply collaborative effort. It required multiple individuals working in concert, some holding lines taut, others citing alignments, their collective focus turning the construction site itself into a giant, living diagram. Accuracy was verified in the most direct way possible. by checking the symmetry of the lines from multiple vantage points and adjusting until every angle met the eye. In India, this knowledge was formalized in texts known as the Sulba Sutras, which provided detailed instructions for constructing complex sacrificial altars of specific areas using nothing but cords and stakes. The methods for creating perfect squares and rectangles were laid out with step-by-step clarity, proving that sophisticated mathematical ideals could be realized through purely physical, hands-on means. The enduring consistency we see in ancient structures from Britain to the Indus Valley is a direct testament to the reliability of these techniques. This raises a profound question for our own time, where mathematics is often taught as a series of abstract symbols on a page. How might our understanding of geometry and collaboration be transformed if we learned it as these builders did, not just as a mental exercise but as a full-body, tactile experience where the truth of a right angle is felt in the tension of a rope and confirmed by the shared sightline of your team? This physical verification was the final, crucial step, ensuring that the lines on the ground matched the perfect vision in the mind. A water-filled trench became the ancient world's most reliable level. Surveyors would dig shallow channels around the entire perimeter of a massive temple platform and fill them with water. Since water always seeks its own level, they now had a continuous, unbreakable reference line. By measuring down from the water's surface at countless points across the vast foundation, crews could ensure that every single stone was set to the exact same height, creating a perfectly flat plane that stretched for acres. This was not a one-time check, but a continuous process of verification, the same principle of using nature's constants applied to celestial alignments. A shadow pole placed at the center of a sacred circle or at the end of a long processional way allowed priests to recheck their alignments as the sun traveled across the sky. The moving shadow acted as a giant sundial, its path confirming that the axis of their temple was still pointing true. This built-in redundancy was a hallmark of their methodology. Critical distances were often measured by 2, sometimes 3 separate teams working independently. When their results matched, confidence was absolute. When they differed, it signaled a need for recalibration long before any stone was permanently set. This culture of quality control extended to the sculptors' workshops. Before a single major feature was carved on a colossal statue, a grid of fine guidelines was meticulously incised into the stone block. These lines were not part of the final artwork. They were a 3-dimensional map, a scaling system that allowed the artist to carve with confidence, knowing the exact proportions for every curve and angle. As the work progressed and the form emerged from the stone, these guidelines would be carefully polished away, leaving only the perfect, harmonious figure behind. On the construction site itself, feedback was constant and tactile. A simple frame with a plumb line suspended from its apex could be placed against any rising wall. If the plumb line hung perfectly centered between the frame's legs, the wall was true. If it was off, the error was visible to everyone, demanding an immediate correction. Story poles, long stakes marked with the standard cubit measurements, were used by foremen to verify that every team working on every part of the structure was adhering to the same universal scale. This relentless, multi-layered checking ensured that a tiny misalignment in one section did not compound into a catastrophic failure elsewhere. What does this teach us in an age of digital precision? Our laser levels and GPS coordinates are undeniably accurate, but they can also create a false sense of infallibility, distancing the craftsman from the material. These ancient methods required a physical, intimate engagement with the work, fostering a culture where every individual was personally responsible for the quality of their contribution. This meticulous verification was the final safeguard, the practice that turned ambitious designs into enduring realities. The arch is a perfect marriage of form and force, a shape that nature itself perfected in the curve of a stone bridge or the dome of a cavern. Roman engineers observed these natural wonders and translated their logic into the soaring aqueducts that strode across their empire. By channeling the immense weight of stone and water along a graceful, curved pathway, the arch redirected downward force into outward thrust, which was then captured and contained by the heavy piers on either side. This brilliant principle allowed them to span vast distances without a single support in the middle, turning what would have been a crushing load into a self-supporting structure of incredible strength. This was not an isolated discovery. Centuries earlier, in the Mycenaean tombs like the famed treasury of Atreus, builders used a different but equally brilliant technique, the corbelled arch. Here, each successive layer of stone was set slightly inward, overhanging the one below, until the walls met at the peak. This created a towering, beehive-shaped chamber that relied entirely on the stable, interlocking force of compression, each block holding its neighbor in a perfect, balanced grip. The path to this confidence was paved with small-scale experimentation. Before committing to a full-sized dome or bridge, engineers would construct scale models from wood or clay, testing how different shapes managed stress. They learned through trial and observation that a wider base could better resist the outward push of an arch, a lesson visibly applied in the gradual thickening of a pyramid's core as it descends toward the ground. This empirical testing was their version of computer simulation, a slow, hands-on process of discovery that taught them how to prevent collapse by working with the inherent forces of physics, not against them. This deep understanding of load distribution unlocked the creation of breathtaking interior spaces. In the hypostyle halls of Egyptian temples like Karnak, the forest of massive columns was not arranged at random. Their spacing was a masterclass in calculated support, placed at precise intervals to create the widest possible open floor plan while ensuring the heavy stone roof slabs above would remain securely suspended for millennia. The sheer longevity of these structures is the ultimate validation of their sound engineering. It makes you wonder, does our modern reliance on computer-aided analysis, for all its precision, sometimes distance us from the intuitive, physical feel for how forces move through a material? The ancient approach was rooted in a tangible dialogue with weight and balance, and this practical genius was often layered with profound meaning. The arch was not just a functional solution, it was a symbolic gateway. The soaring vault of a tomb was a passage to the heavens, and the columns of a temple were stone representations of a sacred grove. The structure's strength was inseparable from its spiritual significance, proving that the most enduring engineering always serves a purpose deeper than mere utility. A carved panel on the Parthenon was never merely decoration. It was an integral piece of the temple's stone skeleton. The sculptors who shaped the metopes and the engineers who calculated the load of the entablature were partners in a single, unified vision. Structural elements like the triglyphs, those grooved blocks in the frieze, served a dual purpose. Their vertical channels were a defining aesthetic of the Doric order, but they also marked the ends of the ceiling beams hidden within the structure, a perfect marriage of revealed form and concealed function. This philosophy of integrated design ensured that beauty inherently strengthened the whole. Across the world, the towering gopurams of Indian temples are covered in a breathtaking profusion of carved deities and mythological scenes. This intricate stone lacework is far from superficial. The deep undercutting and complex patterns actually help to break up and redistribute the immense weight of the gate tower, allowing it to soar skyward without collapsing under its own mass. For these master builders, there was no distinction between the artist and the engineer. They were one and the same. The goal was a holistic practice where mathematical precision served artistic expression, and artistic form followed structural logic. This synergy extended to a deep understanding of human perception. The Parthenon's famous optical refinements, its gently curving floor and subtly swelling columns, were engineered precisely because the builders knew that perfectly straight lines would appear to sag to the human eye. They designed not for the abstract grid of a blueprint, but for the lived experience of the person standing in the temple's shadow, ensuring the structure felt perfectly balanced and alive. This created buildings that were not just physically stable, but spiritually and emotionally resonant. A visitor would feel the harmony intuitively, a sense of rightness that transcended simple geometry and touched something deeper within. What can our own era of hyper-specialization learn from this seamless collaboration? When architects, artists, and engineers operate in separate silos, we risk creating structures that are either functionally sterile or aesthetically shallow. The ancient model challenges us to rebuild those bridges, to see design as a single, interdisciplinary conversation aimed at elevating the human spirit. To coordinate such a complex ballet of diverse talents required more than shared vision. It demanded a shared schedule. The entire endeavor relied on a sophisticated understanding of time itself, guided by celestial calendars that dictated the rhythms of work and the moments for sacred dedication. The rhythm of the sun and the moon dictated the tempo of construction. Ancient engineers did not simply build. They orchestrated their entire workflow around the predictable patterns of the sky and the earth. In Mesoamerica, inscriptions suggest that the critical task of laying a temple's foundation was often timed to coincide with the spring equinox. This was not a random date, but a moment of celestial balance, chosen to imbue the structure with cosmic harmony from its very inception. The longer days of sunlight that followed provided maximum working hours, while the stable, dry weather of the season offered ideal conditions for the precise surveying and leveling required. The entire labor force, from the lowliest carrier to the master sculptor, moved to the beat of a calendar that was both a practical tool and a sacred text. This deep integration of time and task transformed natural cycles from potential obstacles into powerful allies. In Egypt, this synchronization was a matter of survival and efficiency. The civilization's calendar was intrinsically linked to the annual flooding of the Nile. The inundation period, when farming was impossible, freed up a massive agricultural workforce for state projects. More ingeniously, this was precisely when the water levels were at their highest, creating a network of natural canals that reached right to the edge of the Giza Plateau. The very same floodwaters that fertilized the fields also became the liquid highways for transporting colossal stone blocks directly from the quarries to the construction site by boat. This was logistical genius on a monumental scale, turning a seasonal challenge into the engine of national achievement. The ability to predict these cycles required generations of meticulous observation. Priests and astronomers maintained detailed records of lunar phases, solstices, and the helical rising of stars, compiling a body of knowledge that allowed them to forecast the seasons with remarkable accuracy. These calendars did more than just schedule labor. They also marked the dates for the consecration ceremonies that sanctified each new phase of construction, weaving spiritual significance into the very fabric of the project's timeline. This holistic approach to time management presents a powerful question for our modern era of relentless 24/7 productivity. In our drive to conquer time with artificial deadlines and constant availability, have we severed our connection to the natural rhythms that could actually make our work more sustainable and profoundly more effective? The ancient model reveals that true efficiency is not about fighting time, but about flowing with its current, harnessing its predictable energies to achieve goals that feel not just built but destined. A master mason never wrote down the secret to setting a perfect keystone. He showed his apprentice, guiding the young man's hands to feel the subtle shift of weight as the stone settled into its eternal place. This was the true engine of ancient engineering, a living chain of knowledge passed directly from one generation to the next through the intimate ritual of apprenticeship. In the medieval guilds of Europe, this system was formalized into a rigorous journey from apprentice to journeyman to master. A young boy would spend years mixing mortar and moving stones, learning not just the craft but the culture of the site, the unspoken language of teamwork, and the sacred responsibility of building for the divine. The most sophisticated techniques for vaulting a cathedral ceiling or carving a gargoyle were guarded secrets, transmitted through demonstration and correction, ensuring that quality control was woven into the very fabric of learning. Before the guilds, in cultures without written language, this preservation took even more ingenious forms. Vital knowledge about which types of timber resisted rot, how to find the best clay for bricks, or the precise astronomical timing for planting and building was encoded into the rhythm of songs, the structure of myths, and the steps of ceremonial dances. A ritual performed before the foundation of a house might contain a coded instruction for aligning the walls to the winter sun. The story of a hero's journey could map the correct proportions for a fishing boat capable of weathering a storm. This interweaving of practical information with cultural memory made the knowledge resilient, ensuring it was repeated, remembered, and revered by the entire community. For cultures with writing, the preservation was more direct but no less deliberate. Scribes in the royal courts of Egypt and the temple libraries of Mesopotamia meticulously recorded technical data on papyrus scrolls and clay tablets. These were not merely lists of kings, but practical archives containing mathematical tables for calculating volumes of stone, lists of standardized measurements, and even diagrams for complex pulley systems. The survival of these records allowed an engineer from one dynasty to stand on the shoulders of a master who had lived 500 years before, creating a cumulative wisdom that refined techniques over centuries without losing the core principles. This is why we can trace the evolution of the Greek temple from its bulky, archaic forms to the sublime proportions of the Parthenon, a slow, deliberate march toward perfection powered by this unbroken chain of learning. The stark contrast emerges when such a system fractures. The Roman recipe for their revolutionary underwater concrete, a marvel of material science, was lost for over a millennium after the empire's decline, a technology that simply vanished from human use because the workshops and the master-apprentice lines that sustained it disappeared. This historical silence speaks volumes about the fragility of knowledge. It forces a critical reflection on our own digital age, where we store everything in the cloud, believing it to be permanent. But what happens if the context for that data is lost, if no one is left who understands the principles behind the code? The ancient model suggests that true preservation is not just about storing information, but about nurturing the living, breathing, hands-on practice that gives that information its meaning and its power. The Great Pyramid of Giza stands as a silent testament to a level of precision that borders on the impossible. Across its vast base of 230 meters, the foundation is leveled to within just 2.1 centimeters. To put that in perspective, over an area larger than 5 football fields, the entire stone platform deviates less than the width of your thumb. This was not achieved by chance, but through a method as simple as it was brilliant. Engineers likely excavated a network of shallow trenches across the bedrock and filled them with water. Because water always finds its own level, these channels became a universal reference, allowing teams working hundreds of feet apart to carefully chip the limestone base down to a single, perfect horizontal plane. This foundational flatness was absolutely critical, as the slightest tilt would have been magnified into a catastrophic error over the pyramid's immense height. Achieving this perfect level was only the first step. Each of the four sides aligns to the cardinal directions with a minuscule error of just 0.05 degrees. This is not just close, it is unnervingly exact. The leading theory suggests that ancient astronomers used sighting tubes, perhaps made from hollow reeds, to focus on a single circumpolar star as it crossed the meridian. By tracking its path over many nights, they could establish a true north-south line with breathtaking accuracy, a line that became the unshakable spine of the entire project. Then came the geometry of the slope. Every one of the four faces rises at the same consistent angle of 51.5 degrees. This was no guesswork. Egyptian mathematics used a concept called the sect, which defined a slope by the horizontal distance for each cubit of vertical rise. The builders at Giza applied a single, standardized sect to govern every single course of stone, ensuring the pyramid would taper upward in perfect, harmonious symmetry. The final layer of this precision lies in the stones themselves. The massive casing blocks, now mostly gone, were fitted together with joints often less than ½ millimeter wide. This was accomplished through meticulous on-site dressing. After a block was roughly set, masons would use stone pounders and abrasive sand to slowly grind the facing surfaces against each other, a painstaking process of iterative refinement. The resulting fit was so tight that the entire structure was said to have appeared as a single, gleaming white plane from a distance. This case study beautifully illustrates how the Egyptians wove together astronomical observation, geometric principle, and masterful material craftsmanship into one unified system. Yet for all we understand, profound questions remain. How did they coordinate thousands of workers to maintain such tolerances over a 20-year period? What specific tools allowed for the final polishing of the casing stones to a mirror finish? The pyramid sets a benchmark for ancient precision, a standard we find echoed in other wonders, from the interlocking walls of Sacsayhuaman to the celestial alignment of the Teotihuacan complex. High on a razorback ridge in the Andes, the granite stones of Machu Picchu fit together like a colossal three-dimensional puzzle. The Inca technique responsible for this marvel is known as ashlar masonry, a dry stone construction method where every block is individually shaped to interlock perfectly with its neighbors. The result is a wall with no gaps, a solid stone tapestry woven without a single drop of mortar. This was not just for aesthetic appeal, it was a brilliant seismic innovation. When an earthquake strikes, a rigid mortar-bound structure is brittle and prone to cracking. But the walls of Machu Picchu are designed to dance. The stones in a well-built ashlar wall can shift and shudder during a tremor, moving just enough to dissipate the Earth's violent energy, and then, as the ground stills, they settle back into their original locked position. This built-in flexibility turned the entire city into a resilient, living entity capable of absorbing shocks that would level modern buildings. The craftsmanship required for this was immense. Using only stone hammers and bronze tools, masons would spend weeks, sometimes months, on a single block, patiently pecking and abrading the hard granite until its unique contours matched the stones already in place. The final fit was so precise that the seams between blocks are often invisible, defying the insertion of even the thinnest knife blade. This time-consuming process stands in stark contrast to our modern emphasis on speed, yet it created a durability that has endured for over 5 centuries. Beyond the individual walls, the city's very layout is a lesson in harmony. The builders did not flatten the mountain to suit their design, they allowed the mountain to dictate the design. Structures and plazas are carefully oriented to frame the sacred peaks of the surrounding apus, the mountain spirits, and key buildings align with the rising and setting sun during the solstices. This integration of celestial and terrestrial symmetry shows a culture that saw no separation between the built environment and the natural world. This profound connection was supported by invisible genius. A complex network of drainage channels runs beneath the terraces and foundations, carefully carved from stone to direct the relentless mountain rains away from the structures. This prevented water from pooling and eroding the foundations, ensuring the city would not be washed down the steep slopes it so gracefully inhabits. The entire achievement becomes even more remarkable when you consider the constraints: no iron tools, no wheels for transport, no written language to convey complex blueprints. Machu Picchu stands as a powerful testament to what is possible when human skill works in deep partnership with the environment. It forces a compelling question for our own architects and engineers, especially in earthquake-prone regions. In our quest for rigid, unyielding strength, have we overlooked the wisdom of flexible, adaptive design that learns from the very land it stands upon? This ancient city reminds us that true resilience is not about resisting nature's forces, but about learning to move with them. The Parthenon's columns are not straight. They curve almost imperceptibly, a secret known only to the stone itself and the architects who designed it. Ictinos and Callicrates understood a profound truth about human vision, that perfectly straight lines can appear to sag under the weight of their own scale. To correct this optical illusion, they introduced a gentle swelling in the middle of each column, a feature called entosses. This subtle bulge makes the columns appear taut and evenly weighted, as if bearing their massive load with effortless strength. The entire platform of the temple also bows upward in the center, another calculated curve that prevents the long stone floor from looking as though it dips. Even the corner columns were given special treatment, made slightly thicker and placed a bit closer to their neighbors. This compensated for the bright, open sky behind them, which would otherwise make them seem thinner and more distant than the columns set against the shaded background of the temple walls. Every single one of these refinements was governed by a proportional system derived from the golden ratio, approximately 1.618. This mathematical constant dictated the relationship between the width and height of the columns, the spacing between them, and the dimensions of the triangular pediment above. The result was a building where every element, from the largest column to the smallest carving, related to every other in a perfect visual harmony. The choice of material was equally deliberate. They used Pentelic marble quarried from nearby Mount Pentelicon. This stone is not only strong and workable, allowing for the finest detailing, but it also contains tiny crystals of iron that have oxidized over centuries. This gives the temple its famous luminous, honey gold glow in the Athenian sun, transforming the entire structure into a living sculpture that changes with the light of day. This was engineering that served human perception, a masterful blend of mathematical rigor and psychological insight. The architects were not just building for the gods, they were building for the people who would stand in its shadow and feel an instinctive sense of balance and beauty. In our modern world of computer-aided design and laser-straight lines, what have we sacrificed of this intuitive, human-centered approach? The Parthenon challenges us to consider whether true perfection lies not in abstract measurement, but in how a structure makes us feel, a lesson in crafting spaces that resonate with the eye and the spirit long after the builders are gone. The silent, steady nature of water provided a perfect physical constant for ancient engineers. A simple trench dug around the perimeter of a massive foundation and filled with water created an unbreakable level plain, a reference that could be used by countless workers across a sprawling site. The Romans refined this principle into a sophisticated instrument called the chorobates. This was a long, wooden bench with a precisely carved groove running along its top. By filling this groove with water and ensuring the surface was perfectly still, a surveyor could establish a true level line. Legs with plumb lines at each end verified that the entire device was standing upright, allowing engineers to measure the minute gradients necessary for their aqueducts to maintain a steady, gentle flow for miles. This was not a matter of convenience but of absolute necessity. A slope too steep would erode the channel, while one too shallow would stop the water's movement entirely. The same principle of communicating vessels, where water in connected channels always settles to the same height, allowed teams to transfer a level point across valleys or over hills, coordinating their work across impossible distances without ever losing the shared horizontal plane. In Egypt, the extensive network of canals built for transport may have served a dual purpose. As barges carried stone blocks toward a pyramid site, the still water in those canals could have provided a ready-made, miles-long leveling guide, integrating the logistics of supply with the precision of engineering. This deep understanding of hydrology was woven directly into city plans. At Mohenjo-Daro in the Indus Valley, every street and house was equipped with an elaborate, covered drainage system that channeled wastewater away from living spaces, demonstrating a proactive approach to public health and urban management that was centuries ahead of its time. The reliability of these water-based tools made them indispensable, a natural technology that never failed or required calibration. In an era before spirit levels, water was the ultimate arbiter of truth. This ancient reliance on a simple, abundant resource offers a powerful lesson for our own time. How might communities with limited access to complex technology use these very same principles to build schools, clinics, and clean water systems today? The ingenuity of the past points toward a future where we once again learn to work with the fundamental forces of nature, rather than always struggling to overcome them with expensive machinery. A single whisper on the stage of the theater at Epidaurus could be heard with perfect clarity by a person sitting in the very last row high above. This was not a fortunate accident of the landscape, but a masterpiece of acoustic engineering carved in stone. The architects achieved this miracle of audibility through a precise geometric design, where the slope of the seating and the shape of each step were calculated to act as a perfect sound filter. The stepped rows of stone benches broke up and absorbed the lower frequencies of background noise, the rustling of the crowd and the wind, while simultaneously reflecting the higher frequencies of the human voice directly upward. This created a natural amplification system that required no electricity, only an impeccable understanding of how sound waves behave in space. The entire theater became a giant resonant shell, turning the spoken word into an intimate experience for thousands. This principle of designing for the ear was applied in sacred spaces as well. In many Indian temples, the dimensions of the inner chambers and the materials of the walls were chosen to create specific resonant properties. The reverberation time, the way a chant or a struck bell would hang in the air, was a calculated feature. The space itself was tuned like a musical instrument to enhance ritual music and prayer, making the auditory experience a fundamental part of the spiritual encounter. This multisensory approach reveals a design philosophy that was profoundly holistic. Ancient engineers were not just building structures to be seen, but to be heard and felt. They considered the full human experience within a space, understanding that true harmony engages all the senses at once. This integration of acoustic science with architectural form required a deep, intuitive grasp of physics married to an artist's feel for human perception. In our modern world of digital sound systems and acoustic paneling, have we lost the art of building sound directly into our environments from the very first blueprint? These ancient enhancements show a completeness of vision, where a building was not merely a shelter but a living, responsive entity designed to shape human experience in the most profound and balanced ways. The wisdom of the ancients is quietly reshaping our modern world. The very same principle that aligned a temple to the winter solstice sun is now a cornerstone of sustainable design, known as passive solar alignment. Architects today deliberately orient buildings to capture the low winter sun for natural warmth, while using strategic overhangs to block the high, harsh summer rays. This simple, low-energy approach dramatically cuts heating and cooling costs, proving that a 3,000-year-old idea can be more efficient than the latest mechanical system. We see a similar revival in material science inspired by the Romans. Their lime mortar was not just a glue for stones, it possessed a remarkable self-healing property. When tiny cracks formed, rainwater would seep in and react with unmetabolized lime particles, forming new crystals that literally knitted the fissures shut. Modern researchers are now developing concrete blends with encapsulated bacteria or polymers that mimic this ancient process, creating materials that can repair their own wear and tear, potentially saving billions in future maintenance. The geometric harmony of the Parthenon or the pyramids has also found a new home in the digital realm. The complex algorithms that drive computer-aided design and three-dimensional printing often draw upon the very same proportional systems and structural logic that ancient engineers encoded in stone. Software can now generate incredibly efficient architectural forms by applying the timeless rules of sacred geometry, building bridges between the intuitive genius of the past and the computational power of the present. This legacy is not about nostalgia, it is a practical toolkit for the future. In regions with limited resources or in projects with deep environmental concerns, these low-tech, high-impact solutions offer a path forward that is both affordable and profoundly resilient. The global vernacular architecture movement actively learns from these methods, constructing comfortable, durable homes using local earth, stone, and timber, just as ancient builders did. This prompts a vital question for our high-tech era. As we face global challenges from resource scarcity to climate change, could the most advanced solutions be found not in inventing something entirely new, but in rediscovering the deep, empirical wisdom we left behind? The enduring power of these techniques reminds us that true innovation is not always about moving forward, but about connecting with the timeless principles that have always worked in harmony with our world. A modern team of engineers struggles to move a 1-ton block of granite using only ropes and logs. This is not a failure, but a deliberate experiment in the growing field of experimental archaeology. By reconstructing ancient tools and techniques, researchers are building working-scale models of pyramids and Roman arches, transforming historical theories into tangible, testable realities. These hands-on projects provide answers that dusty scrolls and fragmented artifacts cannot. For instance, experiments using reconstructed dolerite hammers on granite have shown that shaping the famous Stonehenge bluestones was not only possible but efficient, with a small team making significant progress in a matter of days. This practical research generates invaluable data on labor, time, and the inevitable challenges ancient crews would have faced, turning abstract concepts into measurable facts. At sites like Ollantaytambo in Peru, experimentalists have demonstrated how massive stones could have been transported up steep slopes using a combination of earthen ramps, rope levers, and carefully placed rollers. Each successful lift or perfect fit achieved with these primitive methods is a powerful validation of the sophistication they are trying to understand. This approach closes the gap between what we think happened and what actually worked, breathing life into the silent logic of ancient blueprints. As these experimental methods grow more sophisticated with motion capture technology and stress sensors, what long-held mysteries of construction might finally be solved? This empirical bridge to the past does more than confirm old ideas. It actively uncovers a forgotten caliber of human ingenuity, preparing us to gather the full meaning of these timeless lessons. This journey through ancient engineering reveals a timeless truth that true precision comes not from complex gadgets, but from a deep and patient partnership with the world. We have seen how celestial patterns provided an unerring compass, how simple ropes and water channels translated cosmic order into perfect geometry on the ground. These builders did not conquer nature with force, but listened to its rhythms, using the predictable swing of the stars and the constant level of water as their most reliable guides. Their mastery was in the creative application of fundamental principles, turning an understanding of weight, balance, and proportion into monuments of breathtaking harmony. In our current era, we confront immense challenges, from a changing climate to the strain on our planet's resources. The ancient approach offers a powerful alternative to our energy-intensive methods. Their low-tech, high-wisdom solutions, built with local materials and designed for resilience, provide a blueprint for a more sustainable way of building and living. They remind us that innovation is as much about rediscovering lost efficiencies as it is about inventing new ones. The next time you look upon a photograph of the Great Pyramid or walk through the ruins of an ancient temple, see more than just old stones. See a masterclass in human ingenuity, a testament to what we can achieve when we blend observation with purpose. We would love to hear which technique resonated most with you. Was it the celestial alignments, the elegant geometry, or the profound material wisdom? Share your thoughts below, and if you enjoyed this deep dive into the mysteries of history, subscribe for more journeys into the past. For the greatest secret these ancient builders left behind may be the quiet realization that the most advanced tools we need for a better future have been here all along, waiting for us to remember how to